Good morning. So, we are going to continue with our discussion on normal density and discriminant function, which we started in our last class. So, in the last class we said that the discriminant function is given by Gix is P ln Px given omega I plus log of a priori probability, that is P of omega I, where omega I is the ith class. Okay. And if we replace this probability density function Px given omega I by a normal density having the covariance matrix as sigma I and the mean vector as mu I, that is P of x given omega I, if we write in this form 1 over 2 pi to the power b by 2 So, this is a multivariate normal density function where the feature vectors x are actually d-dimensional vectors. So, taking this form of probability density function, normal probability density function, the discriminant function Gix becomes of the form minus half into x minus mu I transpose sigma I inverse into x minus mu I minus d by 2 So, this becomes the discriminant function when we assume that the probability density function, the associated probability density function is a multivariate normal density function. And we have said that depending upon this covariance matrix sigma I, we can have different types of discriminant functions. So, we will see those cases that if this covariance matrix sigma I takes different form, then what are the forms of the discriminant function, or what is the architecture of the decision boundary between two different classes that vary depending upon the covariance matrix sigma I for the different classes. So, the first one that we will consider is the simplest form. So, we will put that as case 1, when sigma I, that is the covariance matrix, is of the form sigma square I, where this I is nothing but an identity matrix. That is, it is a diagonal matrix where only the diagonal elements are ones and the rest of the elements are zeros. And so on. Okay. So, obviously, you find that when this covariance matrix sigma I is of the form sigma square into I, where I is the identity matrix, that means we have only the diagonal elements, which gives only the variance of the individual components. Okay. And the variance of all the components are same, which is equal to sigma square. and the off diagonal elements are equal to 0, which indicates that sigma ij is equal to 0. That means the components, different components are statistically independent. Okay. So when a covariance matrix becomes like this, so this is nothing but the case when the feature vectors or the points belonging to the same class, they actually cluster in a hyperspherical space. Okay. And the shape and size of all different clusters they are same, because the variance is same. So all the different clusters belonging to different classes, the points belong to the hyperspherical space and they are of same size. So that is what is meant by this sort of covariance matrix. Now here you find that if the covariance matrix is like this, then the determinant of sigma I, that is for every class, it is nothing but sigma to the power 2d, where this lowercase sigma is the standard deviation of independent components. It is simply because I have a d by d dimensional identity matrix, okay, which is multiplied by sigma square. So I have a diagonal matrix where only the diagonal elements are equal to sigma square and the off diagonal elements are all zeros. Okay, and I have d number of diagonal elements. So the value of the determinant is nothing but product of all the diagonal elements, which is nothing but sigma to the power 2d. Okay, and it is also quite obvious that inverse of the covariance matrix, that is sigma inverse, sigma I inverse, will be nothing but 1 upon sigma square into identity matrix I. Okay. So when I have this, in this case 1, that covariance matrix is same for all different classes. Okay. In this case, having this simplified form, this discriminant function gix, you can compute, it will simply become minus x minus mu I square into divided by 2 sigma square plus ln p of omega I. So what is this term? This is nothing but distance square So this is nothing but the squared distance of sample x from the mean vector mu I. Okay. So in the situation that if all the classes are equally probable, that is ln p omega I is same for all the classes, then this term becomes irrelevant in the discriminant function. So my discriminant function is simply this equation. Okay. And this being the distance square from the mean of the vectors, you find that it becomes a minimum distance classifier. Okay. Because this term will be maximum when this term is minimum, because it is negative. Okay. And x minus mu I square being the squared distance from the mean vector and all the classes having same variance sigma square. Okay. You find that this simply becomes a minimum distance classifier. So given a feature vector x, you simply compute its distance from the mean vectors from all different classes. Okay. And whichever distance is minimum, that is the nearest mean of the classes, this x will be classified to that particular class. Okay. Now, if we, and here you find that even if this p of omega I is present, that means the a priori probabilities of different classes are different, they are not same. Then for a sample point which is equidistant from all the cluster means, all the class means, the decision will actually be biased by this term log of p of omega. Okay. Now, if I go for expansion of the term discriminant function, then you find that this gix the discriminant function is simply of the form minus half x minus mu I transpose sigma I inverse into x minus mu I plus log of p omega I. Okay. Why I am writing like this is, in this expression you find that minus d by 2 log of 2 pi, this is independent of class, this is a constant term. So I can simply ignore this from the expression of the discriminant function, because this term anyway is not going to influence our decision, because for all the classes, for the discriminant functions of all the classes, this term is going to be present. Okay. Similarly, this determinant of sigma I, that is covariance matrix, in this particular case, which is nothing but sigma to the power 2d, this is also same for all the classes. Okay. So this also becomes irrelevant in the discriminant function, because for all the discriminant function the same term will be present and the value of this term will be same. Okay. So what will discriminate among the classes is the first term and the last term. Okay. So we have this simplified discriminant function expression when sigma I is equal to sigma square into identity matrix I. Okay. So if I expand this term, you find that this expression can be written as minus 1 upon 2 sigma square into x transpose x minus 2 mu I transpose x plus mu I transpose mu I plus log of p omega I. Okay, this is nothing but expansion of this term, where the sigma I inverse we have said is 1 upon sigma square into identity matrix. So that is why here I get 1 upon 2 sigma square, and if I simply expand this, I get this particular expansion. Okay. Now again here you find that the first term within the bracket, that is this x transpose x, this is also independent of class. For all values of I in all the discriminant functions g I x, the same term will be present. Okay. And this sigma square being same for all the classes, this term x transpose x upon 2 sigma square, that also becomes a redundant term. It is not really deciding to which class this x will belong. So I can also ignore this term from the discriminant function. Okay. So by ignoring this, the discriminant function becomes a simplified form like this: g I x will be equal to minus 1 upon 2 sigma square into minus 2 mu I transpose x plus mu I transpose mu j plus log of p omega I. Okay. And this, you find that I can write this in the form wi transpose x plus wi naught. Okay. Where you will find that this wi is simply 1 upon sigma square mu I, and wi naught is nothing but minus 1 upon 2 sigma square mu I transpose mu I plus log of p omega I. Okay. So this particular expression can be written in this form wi transpose x plus wi naught, where this Wi is nothing but 1 upon sigma square into mu I, and Wi naught is minus 1 upon 2 sigma square mu I transpose mu I plus log of p omega I. Okay. So, if you look at this expression, that finally how we get the discriminant function expression for Gix, which is Wi transpose x plus Wi naught. This is nothing but a linear equation. Okay. So, in this simplified case, when all the covariance matrices for all the classes are same and is of the form sigma square into I, the discriminant function simply becomes a linear equation. Okay. So, this is, and if we have a classifier where the discriminant functions which classify based on these such linear equations, that is called a linear machine. Okay. So, a classifier which uses the linear discriminant functions to decide about the class belongingness of an unknown vector, that is called a linear machine. So, this will form a linear machine. Okay. So, that is about the discriminant function of an individual class or ith class. Now, if I want to find out the decision boundary between two different classes, so I have two classes, class omega I and class omega j. So, I have two different classes. So, what will be the nature of the decision boundary between these two classes, the ith class and the jth class? Okay. So, you have find that if I want to find out the decision boundary, on the decision boundary Gix for a feature vector lying on the decision boundary, Gix will be equal to Gjx. Okay, because that is the case, I mean that is the situation which differentiates between two different classes. If Gix is greater than Gjx, x will belong to class I. If Gjx is greater than Gix, then x will belong to class j. Okay. And the situation that Gix is equal to Gjx, that tells you the decision boundary. That means the equation of the decision boundary is simply given by Gix minus Gjx, that is equal to 0. Okay. This is the equation of decision boundary. Okay. And we have just seen that Gix is nothing but Wi transpose x, it is a linear equation, plus Wi0. Similarly, Gjx will be Wj transpose x plus Wj0. Okay. So, in this expression, if I replace Gix by this and Gjx by this, okay, so I simply get the equation as Wi minus Wj transpose x plus Wi naught minus Wj naught, that is equal to 0. Okay. And here, if I replace Wi by the value of Wi, which is nothing but 1 upon sigma square mu I, and Wi naught by the value of Wi naught, which is nothing but 1 upon 2 sigma square mu I transpose mu I plus log of p of omega I, and similarly for Wj and Wj naught. Okay. So, by replacing these values of Wi Wj and Wi naught Wj naught, this expression will simply become 1 upon sigma square mu I minus mu j transpose x minus mu I transpose mu I upon 2 sigma square plus log of p of omega I, okay, plus mu j transpose mu j upon 2 sigma square minus log of p omega j, okay, this will be equal to 0, right. And this same expression, if I go on simplifying, this will lead to a form mu I minus mu j transpose x minus half okay. It is simply the same expression where we have grouped together mu I transpose mu I upon sigma square 2 sigma square and mu j transpose mu j upon 2 sigma square, and grouped together this log of p of omega I and log of p of omega j. So I get this particular expression, okay. And this expression can further be simplified. So I can write it in the form mu I minus mu j transpose into x minus half of mu I plus mu j minus sigma square upon mu I minus mu j square log of this is equal to 0. I can convert this expression into this form where you find that this mu I minus mu j transpose that has been taken out of all the terms. Okay. So when I can write in this form, this is simply of the form W transpose x minus x naught is equal to 0. Okay. Where this term W is nothing but mu I minus mu j, where mu I is the mean vector of the ith class and mu j is the mean vector of the jth class. Okay. And x naught is simply half of mu I plus mu j minus sigma square So what information do we get from this? Here you find that this is W transpose x minus x naught is equal to 0. That is the decision boundary between the ith class and jth class. Okay. Where this W is given by mu I minus mu j, that means it's a vector drawn from the jth mean vector mu j to the ith mean vector mu I, or the line joining mu I and mu j. So that is what is W. Okay. And as the decision surface is W transpose x minus x naught equal to 0. Okay. So the decision surface is orthogonal to the vector joining mu I and mu j. Okay. So the situation is simply like this, that if two vector positions are, say I have mu I over here and mu j over here, and this is the line joining mu I and mu j. Okay. The decision surface will be orthogonal to mu I and mu j. Okay. And because it is the linear equation, so the decision surface is a hyperplane which is orthogonal to the line joining mu I and mu j. Okay. And if this term is equal to 0, that is when the a priori probabilities p omega I is equal to p omega j, okay, then this term is equal to 0, right. This orthogonal plane, it passes to point x naught, which is on the line mu I and mu j. Okay. So this is point x naught, right. If this term is 0, in case that a priori probabilities p omega I is same as p omega j, then x naught becomes half of mu I plus mu j. Okay. So this x naught in that case is midway between mu I and mu j, and I have this hyperplane which in this case is nothing but orthogonal bisector of the line joining mu I and mu j. And because it's the orthogonal bisector, again I come back to the same situation, that the kind of classifier that I have is a minimum distance classifier, because if I have an orthogonal bisector of the line joining mu I and mu j, then for all the points which are falling on the side of mu I, its distance from mu I will be less than its distance from mu j. Similarly, for all the points which are falling on the side of mu j, its distance from mu j will be less than its distance from mu I. Okay. And we put the sample x to that particular class from which its distance is minimum. Okay. So when it is an orthogonal bisector, or the a priori probabilities p omega I and p omega j, they are same, then effectively what I get is a minimum distance classifier. Right. So effectively it says that if the probability density functions, the normal probability density functions are like this, again plotting in univariate case, so on this side I put x, and this is p of x given omega I, and suppose this is for omega 1 and this is for omega 2. So if the a priori probabilities p omega 1 and p omega 2 are same, and this is what is my mu 1 and this is what is mu 2. So if the a priori probabilities are same, my decision surface will be at the middle. If the a priori probabilities are more, if p omega 1 is more than p omega 2 a priori probability, then decision surface will be pushed towards p omega 2, that is away from mu 1. if P of x given omega 1, P of omega 1 is greater than P of omega 2, then the decision surface will be pushed away from mu 1. If P of omega 1 is less than P of omega 2, then the decision surface will be pulled towards mu 1. Okay. So, in the simplified case, when all the covariance matrices are same, okay, and they are of the form sigma square into I get such simplified linear classifiers, and the decision boundary between the two classes will be orthogonal to the line joining the corresponding mean vectors. If the two classes are equally probable, that is, if the a priori probabilities are same, then the decision surface is nothing but a orthogonal bisector of the line joining mu 1 and mu 2, in which case the classifier effectively becomes a minimum distance classifier. Okay. Let us take another case, that is case 2. Okay. Here I assume again that all the classes have the same covariance matrix, that is sigma I is equal to sigma. In the first case, we have said that this sigma is of the form sigma square into I. Okay. But now we are not putting that restriction. The sigma or the covariance matrix is arbitrary, but all the classes, samples belonging to all the classes, have the same covariance matrix, though it is arbitrary. Okay. So, in the previous case, we said that the samples are clustered into hyperspherical spaces of equal size. Okay. In this case, the samples will cluster into hyperellipsoidal spaces of same shape and same size. Okay. It will be same shape and same size because the covariance matrix is same. And as the covariance matrix is arbitrary, so in general it will be a hyperellipsoidal space. So, the samples belonging to different classes, they cluster into hyperellipsoidal space of same shape and same size. Is that okay? So, that is the second case. So, here again you find that out of this expression of the discriminant function, the general expression, in the general expression we had Gix is equal to minus half x minus mu I transpose sigma I inverse into x minus mu I minus d by 2 log of 2 pi okay. So, this is the general expression of the discriminant function. Now, here we are saying that sigma I or the covariance matrix is same for all the classes. Okay. So, if it is same for all the classes, then obviously this term, obviously this is a constant term. So, this does not give you any discriminating power, and again this term, this is also same for all the classes because this sigma I is same for all the classes. So, this also becomes irrelevant. So, we are left with Gix is equal to minus half x minus mu I transpose sigma I inverse x minus mu I plus log of p omega I as before. Okay. And here again you find that if this log of p omega I, this also becomes irrelevant, that is if all the classes are equally probable. Okay. Then my discriminant function simply is Gix is equal to minus half x minus mu I transpose sigma I inverse x minus mu I. And we said that this is nothing but a distance function which is squared Moholy-Nagy distance. okay, squared. Okay. So, effectively the classifier again becomes a minimum distance classifier, because this being a distance function, okay, if gix has to be maximum, then this has to be minimum, and x will be put into that particular class for which this term is minimum. So, again it becomes a minimum distance classifier, but the distance that we have to compute in this case is not the Euclidean distance, but the Mahalanobis distance. Okay. So, considering the fact that we will compute Mahalanobis distance, again we have a minimum distance classifier. Okay. So, as we have done before, if we simply expand this term, then again we will find that the discriminant function gix will again be of the form wi transpose x plus wi naught, where in this case, in the earlier case, this wi had a very simple form, that is 1 upon sigma square into mu y. Okay. Now, this wi will be of the form sigma inverse into mu I. Earlier this sigma inverse was replaced by 1 upon sigma square in the first case. Okay. So, now it becomes sigma inverse into mu I, and wi naught is simply minus half mu I transpose sigma inverse mu I plus log of p of omega I. Okay. So, again we find that this term, the nature of the discriminant function, this is again a linear equation, because this is wi transpose x plus wi naught. So, this is again a linear equation. Okay. So, our classifier making use of such linear discriminant functions, that again becomes a linear machine. Okay. Now, using this linear discriminant functions, if I want to find out, as I have done before, that we want to find out the nature of or the structure of the decision surface between two classes omega I and omega j. So, again we will follow the same procedure, that gix minus gjx equal to 0, that is the equation of the decision surface separating the two classes omega I and omega j. And if I follow the same steps, again here you will find that the equation will come in the form w transpose x minus x naught is equal to 0, where this w is given by sigma inverse into mu I minus mu j, and x naught is given by half of mu I plus mu j minus log of p omega I upon p omega j Okay. So, the expression becomes more or less same. I get similar expression w transpose x minus x naught equal to 0. Okay. But this w is nothing but sigma inverse mu I minus mu j. If you remember, earlier case our W was simply mu I minus mu j, and mu I minus mu j is the line or the vector from mu j to mu I. Okay. So, W had the same direction as the vector mu I mu j, but sigma inverse mu I mu j is not in general in the direction of mu I and mu j. Okay. So, as a result, this vector W, which is sigma inverse mu I mu j, this is not in general in the same direction of the vector mu I mu j. Okay. So, you find that from this expression, though my decision surface is orthogonal to vector W, in the previous case W was in the direction of the vector mu I mu j. So, the decision surface was orthogonal to the line joining mu I and mu j. And in this case, because W is not in the direction of line joining mu I mu j, so the decision surface is not in general orthogonal to the line joining mu I mu j. Okay. But the decision surface passes to the point x naught, where the expression for x naught is given by this. Okay. So, here again you find that if P of omega I and P of omega j they are same, then this term becomes 0. When this term becomes 0, then x naught is half of mu I plus mu j. That means it is halfway between mu I and mu j. Okay. So, when the classes are equally probable, the decision surface of the hyperplane passes through the midpoint of the line joining mu I and mu j, but it is in general not a orthogonal bisector. It is a bisector, but not orthogonal. Okay. So, effectively the kind of situation that we will have is, if I have these two means mu I and mu j, this is the line joining mu I and mu j, okay, and the decision surface will be something like this. This is point x naught and this is your decision surface. Okay. So, we still have the linear classifiers, the decision surface between two classes are still hyperplanes, okay, but this is not a orthogonal bisector, or this is not orthogonal to the line joining mu I and mu j. Okay. Now, let us take the third case, which is the most general one. That is, the covariance matrix mu I is totally arbitrary. That means different classes have different covariance matrices. In case 2, we have considered that different classes have arbitrary covariance matrices, but covariance matrices of all the classes are same, though arbitrary. Okay. The first case was the simplest case, where we assume that the different components are statistically independent and individual components have the same variance. Okay. So, this is the most general case where the different classes will have different covariance matrices. Okay. So, over here I do not have any other option, I have to keep all the terms. So, Gix, if I keep all the terms, you will find that it will be of the form x transpose Aix plus Bi transpose x plus Ci0, where this Ai is minus half sigma I inverse, Bi is sigma I inverse into mu I, and Ci0 is given by minus half mu I transpose sigma I inverse mu I minus half okay. So if you find that in the earlier cases where we could remove the quadratic terms, that is term involving x transpose x or x transpose ax, we could have removed that term because x transpose x does not give you any discriminating power. But over here this is x transpose aix, where aix depends upon the value of sigma I, that is the covariance matrix, and different classes have different covariance matrices. So this term x transpose aix now becomes class dependent. Okay, because it is class dependent, it really contributes to decide whether x will belong to class omega I or x will belong to class omega j. So I cannot remove any of the terms, and this expression that I have, it is nothing but a quadratic expression. Okay. So giving you a quadratic classifier. In the earlier two cases we had linear classifiers, in this case we get a quadratic classifier. And using this quadratic classifier, if I want to find out the decision surface between two classes omega I and omega j, the decision surface will be a hyperquadratic. Okay. So it is a quadratic surface in a multidimensional space. Okay. So these are the different cases that we can have, assuming multivariate normal density functions for the samples belonging to different classes. Okay. Let us see an example. Suppose we have points belonging to two classes, one is omega 1, class omega 1 and class omega 2. Okay. The training samples which are provided for these two classes are like this. For class omega 1 it is 2 6, 3 4, 3 8 and 4 6. So these are the training samples which are given for class omega 1. Okay. And the training samples for class omega 2 are given as 3 0. So naturally we are considering a two-dimensional space, and as I said that the examples typically I will take in 2 dimension because I can draw it on a plain paper. Okay. So this is 3 0, 1 minus 2, 3 minus 4 and 5 minus 2. So these are the training samples for the belonging to two classes omega 1 and omega 2 which is given. And it is also said that the a priori probability is p of omega 1 which is equal to p of omega 2, and naturally this is equal to 0.5. Okay. So what we have to do is we have to find out the decision boundary between class omega 1 and class omega 2. Okay. So to find out the decision boundary, I have to find out the discriminant functions between two classes omega 1 and omega 2 and then subtract that, equate that to 0. Okay. Or in general, because I have to compute sigma I, that is the covariance matrix for independent classes, and I do not know what is the nature of sigma I. Okay. So in general I can make use of this expression and go ahead with it, assuming that my surface will be quadratic. In case the surface is not quadratic, all the quadratic terms will get cancelled. Okay. So first what I have to do is I have to find out the mean vector, which is mu1, and mu1 is nothing but I take all these vectors and find out their mean. Okay. So, this mu1 in this case will come out to be 3, 6. You can verify this. Okay. Similarly, for class 2, mu2 will come out to be 3 minus 2. Okay. So, that is the mean vector for class 2. We also have to find out the covariance matrix sigma 1 and the covariance matrix sigma 2. You know how to compute the covariance matrix. Once I get the mean vector, then what I have to do is I have to find out x minus mu into x minus mu transpose, take the summation over all the vectors, then normalize by the number of vectors you have taken. Okay. So, that gives you the covariance matrices sigma 1 and sigma 2. So, if you do it that way, you will find that sigma 1 comes out to be half 0, 0, 2. So, this is the covariance matrix of class 1, and sigma 2, that is the covariance matrix of class 2, comes out to be 2, 0, 0, 2. Okay. So, you find that the covariance matrices of the two classes are different. Okay. And as the covariance matrices of the two classes are different, the classifier is not a linear classifier. It will be a quadratic classifier. Okay. From here, I can compute sigma 1 inverse, which is nothing but 2, 0, 0 and half. From here, you can compute sigma 2 inverse, which is nothing but half, 0, 0 and half. Okay. So, these are the inverses of the covariance matrices. Now, once I get this, I find out G1x which is of the form x transpose A1x plus B1 transpose x plus C1 0. Okay. And the expressions that we have given over here in a quadratic classifier. Okay. Where the value of A1 will be nothing but half of sigma 1 inverse, value of B1 will be sigma 1 inverse mu 1, and value of C1 0 will be minus half of mu 1 transpose sigma 1 inverse mu 1 minus half log of determinant of sigma 1 plus log p of omega 1. Okay. Now, in this case, p of omega 1 is same as p of omega 2. So, this term can be neglected. Even if I keep it on both sides, they will get cancelled. Okay. So, I do not have to really compute this. So, if you compute all these terms and put in this expression, and similarly you find out G2x following similar expressions, and then equate G1x is equal to G2x or G1x minus G2x equal to 0, then you will find that finally the decision surface, I am not going to the detailed calculation, that is a simple one. The final decision surface will come out to be x2 is equal to 3.514 minus 1.12 x1 plus 0.1875 x1 square. Okay. So, you find that the decision surface is really a quadratic. In this case, it is a curve because we are in two-dimensional space. Okay. So, the decision boundary is really a quadratic curve. Okay. Now, if I want to find out how this quadratic curve looks like, I'll simply plot these points on paper, okay, and find out how these surfaces look like, okay. So I have points 2, 6, okay, then I have points 2, 4, sorry, 3, 4. I have 3, 8, 3, 4 is here. This. I have 3, 8, so this is 1 point, this is 1 point, this is 1 point, and I have 4, 6, that is this point. So these are the points which belong to class omega 1, okay. Similarly, for omega 2, I have 3, 0, 3, 0, this is a point belonging to class omega 2. I have 1, minus 2, 1, minus 2, 1 is over here. I have 3, minus 4, that is this one, and I have 5, minus 2, that is this one. So these are the points which belong to class omega 2. So all these reds belong to class omega 1 and the greens belong to class omega 2. Mu 1 is somewhere over here, this is mu 1, and mu 2 is over here, okay. And if you plot this quadratic curve into this space, okay, so this quadratic curve will be something like this. Okay, but I am assuming that I have two components, one is x1, other one is x2. Okay, so you find that I really get a quadratic curve separating the two classes omega 1 and omega 2. So I'll stop here today and we'll continue with other classifiers next day. Thank you.